Yeah, so, and we are already sharing the screen. Is good. Yeah, you can still talk.
Oh, thank you.
Yes, and I think we'll wait another minute and then start. How are things in Oxford?
Yeah, fine. I mean, we're currently a COVID hotspot, but I'm in the fortunate doubly vaccinated category, so I'm not too worried for me. Bit more worried for the young people who haven't yet had 2 jabs. But...
Yes, it is. It is a bit worrying with Johnson's insistence of reopening next week.
We'll see what happens.
Yes.
To be honest, I'm not sure there's that much difference between next week and this week in terms of what's open. So I think it's the steps that have already been taken that are kind of maybe questionable.
Okay, yeah. So I guess from outside it seems like there's some big changes coming, but maybe it's not. Okay, let me start the recording. So, and we have Asaf's second talk today. The third talk, as a reminder, will be on Thursday at the same time. No talk tomorrow. And small comments. So we have a Discord forum. There's a link to that on the OOPS website that you can find. And if you have any questions or queries or requests or anything is unclear, you can ask questions there. And usually someone will answer fairly quickly. Or you can just email Asaf. But okay, Asaf, floor is yours.
Hi, nice to be back. Welcome everybody. So today I will show you parts of the proof, or perhaps all of the theorem that I promised you regarding the local structure. Let me just restate it. So this is together with Yuval Perez. I guess 21. You take a sequence of regular graphs, sequence of connected, let's say all the necessary words connected, so you can draw a uniform spanning tree. I'm reminding you, a spanning tree of a graph is a connected graph on the same set of vertices that touches every vertex with an edge and is connected and contains no cycles. So GN is a sequence of connected finite. Here it will be important for the graphs to be simple. We'll see in a second why. Simple, regular, with degree tending to infinity. Then the UST of GN converges locally, or the local limit of it, to the Poisson one branching process condition to survive. And again, BP is always going to be branching process in this talk, condition to survive. So just a few comments. Why do you need, and just to remind you, what is this object and what is converge locally? Let me not tell you what converge locally is, as I did before. The object at the limit is an infinite random graph where you obtain by taking an infinite discrete array, and on each point you hang a Poisson one. They can be in different sizes, but all finite, a Poisson one independent branching processes. Okay, with the entire tree, right? And this point here is the root, and from this and the statement, this UST converges locally means that what this means is that if X is a uniform vertex of Gn, then the probability that the ball around X in Tn is always going to be the UST of the Gn, the probability that you see a particular tree, like a fixed rooted tree, radius r, right, as your ball of radius r in the uniform spanning tree is the same thing, is the same probability, right, when here you have this Poisson 1 branching process conditioned to survive, right, and this is in the limit, of course. Okay, so for instance, the number of leaves will be 1 over e, the number of vertices in which the path, the ball of radius 3 looks like this will be n over e cubed, 1 over plus smaller order terms, etc., etc. So this way you can tell the frequency of appearances of any fixed tree. Why do we need simplicity? The theorem does not hold without simplicity, and you have simplicity, of course, the simple graph, right? Because if you have d parallel edges, right, a path of length n, and each edge you replace by d parallel edges, right? Then of course, the uniform spanning tree is just going to be a line of length n, right? And it's not random at all, and in particular, it's definitely not this picture. Okay.
Yeah, quick question. So you say that you take X to be a random vertex in G, and if you take a fixed vertex in G, then this doesn't necessarily hold. But does it hold for most vertices? If you take, is it the case that for most vertices?
Yeah, so indeed, what Omer is saying, my statement as I wrote it is an annealed statement where the probability space is both on the tree and on X, but it's no problem. Okay, I'm exaggerating about the no problem. You need to do something, but once you know how to prove this theorem, a rather straightforward second moment argument will give you the quenched version, i.e. for most vertices, you see this behavior for right, almost all the vertices. And there, of course, the proof is robust. There you have quantitative estimates. Unlike for the global structure, as I mentioned earlier, in the previous talk, where we have literally no rate of convergence. All right, and as I promised, the proof.
Can I ask a question?
Yes.
Yeah.
Please. Oh.
Yeah. The regularity is not really important, is it?
It is important. Okay, so here's a good. Thank you for the question. So if you take, for instance, it does not hold with otherwise, right? So if you take, say, a bipartite complete graph that on one side has n over 3 vertices, and on the other side has 2n over 3 vertices, and you put all the edges between them, then what you get is a Poisson half, Poisson 2 alternating branching process. So on the even degrees, on the even generations, it spits out a Poisson half, and on the odd ones, it spits out a Poisson 2. I guess it's not even an odd, right? The first one is random, and then it just changes. So it's not. It really is not the same limit without regularity. Now, I should mention there's an earlier work where if your graph is dense, so the minimal degree is linear, then there's a way. In this particular case, I got this Poisson 1, Poisson half, Poisson 2 branching process. In an earlier work that I didn't mention from 2017, there's a way using graph limits theory and Semeredi regularity. There's a way to look at the graph and guess what is the branching process that the UST will be its limit. Okay, but and in the particular case where you have a dense regular graph, then this theorem tells you that you always get Poisson 1. So it recovers one particular case. Okay. Any other questions about the statement? Yeah, as I said, feel free to, of course, interrupt me. I will be thankful. Okay, so as I promised, the proof is based on electric networks, and in fact, it can be seen as a bunch of facts about electric networks. And let me just make two remarks. So just as I said, I said that last time, the effective resistance between two vertices in a graph is the voltage difference induced if you take a unit current flow from the first vertex to the second, just like we learned in high school physics. It's amazing to think that something there was useful, but I guess it was. Right, so this is one definition, and the nice thing about the effective resistance, and perhaps this is the reason, as I said, that it was discovered by in different areas of math: extremal length, conformal modulus. It's a completely general quantity, even more general than what we're dealing with here: graphs and edges and paths and things like that. And it has all sorts of meanings and difference in the planar setting. It really there really is complete like very nice richness to it that I'm not describing to you here at all. And there are other definitions, right? Why do we even study it? And that's the so just a few comments, so reminders that I will use about electric networks, about electricity or electric networks, and perhaps some notations. This is very standard notation. So if I will write Cij for the conductance, electric conductance on the edge Ij, right? And pi I will not be it will be just the sum of the conductances on edges coming out of I, right? So this is in the, if all conductances are unit, then this is just the degree. And what's the relation to random walk? So of course, if there's, as I told you, there's a voltage is a harmonic function, and harmonic functions, except, harmonic function except for 2 points, always describe to you the value at a point, if you normalize it properly, is the probability when you start from a point that you hit the second vertex before you hit the first vertex. So this is always one way to write, to either define or to prove that it's equivalent to the previous definition. So if you have two vertices, the effective resistance is just 1 over pi a, the probability when you start your random walker from A, that you hit Z before turning to A. Right, so this is right. This is very, and this can be taken also as the definition. Right, so this is very classical. And another classical fact that I will use that. So this really just follows very easily from the definition that I gave you, and it's slightly harder to show the following identity, which is known as the commute time identity. It tells you some identity involving the effective resistance, and this can also be taken to be its definition. So here's the identity. I'm working here and just in the setting of unit conductances. So in unit, so all conductances, unit conductances. If you look at the effective resistance between A and Z, times twice the number of edges, or the sum of the degrees. In general, you can write here just the sum of the pi i's instead of twice the number of edges. This is the expected time the random walker takes to go from A to Z and back. Right, expected time to go to Z and travel back. Right, so this is nice. Observe that this quantity is indeed symmetric, right? Getting from A to Z and back is the same as takes you on expectation. Obviously, same time it takes you to go from Z to A. right? But just one of these terms is not symmetric, right? The expected time from A to Z is not equal to the expected time from Z to A. And you can convince yourself with almost any graph that you will take, or it's easy to construct an example. All right, and what did we prove at the end of, let me remind you, the connections, the basic connection due to Kirchhoff in the 19th century, what we proved, and this is what indeed Kirchhoff proved in his 2Fs. What he proved, if you have, so all my graphs will be finite and connected, right? If you choose an edge E, right, and you want to ask what is the probability that E is in T, then this equals the effective resistance between X and Y. And I've shown to you a cute bijection that shows this. Note that because, right, X and Y, there's an edge between them, right, then this effective resistance is always no more than 1, right? Because in the worst case scenario, the electricity will just flow on that single edge, and then the voltage difference is going to be 1, and clearly the, at least from our physics intuition, this is the worst case scenario. And the electricity wants to go in the most efficient way from X to Y. Right, so this is indeed a number between 0 and 1. What is an immediate corollary of this statement? And this is a corollary that the original proof is somewhat harder, and this is called Foster's theorem. Foster's theorem tells you the following: just that if you go over all the edges of your graph and compute the effective resistance between their endpoints, then this is just the expected number of edges in the uniform spanning tree, which is always the number of vertices, which I will always call n minus 1. Right? So this is an immediate corollary. Right? An immediate corollary. And here is a different way of stating this corollary. Alternatively, right, let's view it as a right, this is a sum over the edges, so we can so what this means is that right, so we can view it as if we're sampling a random edge and checking what is the resistance across its vertices, right? So this is, if I just divide by the number of edges, I get that the expectation of a random edge, x0, x1. I'm writing x0 for not x1, x2 for a reason that will be apparent immediately, or not, right? And this is just n minus 1 divided by the number of edges. And this is, of course, if your graph is when G is regular, G is D regular, and D tends to infinity, right? Then the number of edges is D times n over 2. So what you have here is 2 over D, 1 plus little o of 1. So we have here the basic statistical statement, right? That if you look at the resistance across an edge, the average over all the edges is going to be order 2 over D. But of course, this does not always happen, right? There's no problem of like having a regular graph that looks something like this, right? And here's an edge E that disconnects the graph, and of course the resistance across this edge is really 1, right? If the resistance across an edge is 1, if and only if it disconnects the graph. So the first thing you can ask yourself is right, and I will. Is how many of these can you have when you have a regular graph? How many bridges like this can you have? And you can build an example like this. Okay, perhaps you could put here cliques and things like that, and you get at least it seems that in this example you don't get too many of them. And indeed, with combinatorial. With some combinatorial effort, you can get the correct answer. But if you ask yourself, how many edges do I have in which the resistance across them is at least 1/2, then suddenly the combinatorial estimates do not work very well, because we don't have a characterization, a combinatorial characterization, an edge is a bridge if and only if the resistance across it is 1. But the number that you get here, 2 over d, is this number here is instructive. Why is it instructive? Let's make an observation. So this is in any graph, in any 2 vertices, x and y, they don't even have to be an edge. The effective resistance between x and y is always at least 1 over the degree of x plus 1 over the degree of y, so degree of x. Okay, so I get a little bit tidier, plus the degree of y plus 1. This holds. This is a completely deterministic statement. And in fact, you can erase these plus 1s at the denominator if there is no edge connecting x and y. And the reason is, the reason is not hard to make formal, but the intuitive reason is in my opinion, better, right? When do you get the lowest possible resistance? This is if electricity has flown through x has d neighbors neighboring it. If by any chance the electricity, the unit current has split precisely, right, giving 1 over d to each of these neighbors in this direction, right? And by some miracle, the resistance the current entering y entered exactly at the exactly equally from each of its d neighbors, right? Then you would get that the voltage difference will be 1 over d from here and 1 over d from here, right? And this is a real, this is intuitive, but this is a real statement that you can easily make. The minute you have this feeling of like, oh, electricity would flow the best way, the most optimal way this way, and then you want to prove an inequality, that means that there's just some Cauchy-Schwarz hiding there. You apply it in the right place, and you get this, right? And this is of order, and this is of course 2 over d. So we have a great situation in which we draw a random edge. The expectation of our random variable, right, the resistance across an edge is 2 over d, and you have a uniform lower bound, right? So you cannot have too many edges with high resistance across them, right? And this, of course, you can make immediately formal, and you get the following. Right, this is just you write everything I said, and you get that if you look at if you define n epsilon to be the number of edges exy such that the resistance across them is at least epsilon, right? Then n epsilon, I think about epsilon as fixed or much bigger than 1 over d or 2 over d. Then it is always smaller than n divided by epsilon d minus 2. So epsilon, for this to make sense, has to be bigger than 2 over d. You can think about it as epsilon as log d over d, and already you get a meaningful statement. And this inequality is sharp. So you can definitely build examples like that. So this is an interesting thing when you draw a random edge in your graph with very high probability, right? So let's say it again. So a random edge xy or x naught x1 is with high probability the resistance across it is 2 over d 1 plus little o of 1. For instance, put epsilon to be log d over d, and you get that the edges not satisfying this are sublinear in n. And of course, this I'm using here the little o of 1 is when d tends to infinity. Okay, so this only makes sense when d tends to infinity. Of course, it's not true D is fixed. And our first goal is so this is a classical theorem, Foster's theorem, and the first thing that I want to show you is two extensions of this theorem. And the first extension is what happens if, so a random edge can be drawn as follows, right? I choose a random vertex x0, and x1 is a random neighbor of x0. Right, random vertex. So it's a one-step random walk starting from a uniform point, starting from stationarity, right? X1 is a random neighbor. X1 is a random neighbor. So now take, a k-step random walk, right? And ask yourself, what is so our goal is to show that with high probability, not just if you sample an edge, but if you sample, so this is just the simple random walk k steps. With high probability, the resistance between x nod and xk is also of order 2 over d, 1 plus little o 1. It's high probability. With high probability on the random walk, right? The graph is of course fixed. There's no uniform spanning trees here. And let me show you a proof of this, right? And I'll show you the proof in the case k equals 1, even though we already know it, but it'll be clear after I show you the proof for k equals 1, how to extend it to any arbitrary k. So proof of this thing. Again, all I have to show, for the same reason, all I have to show is that this expectation is of order 2 over d, because by the same reasoning as above, the same observation, we will have a uniform lower bound on the resistance across this edge. So I only have to take care about the expectation. So let's look at the so here's the proof. It's cute. So I fix some x nod, a fixed vertex, and I look at the expected time to return to this vertex in a regular graph. What is this number? So
1 over n.
1 over n is the stationary distribution of the vertex x naught.
Sorry, n.
N, right? The inverse. So this is a fact that is true for any irreducible Markov chain. The probability, not the expected time to return to where you are, is the inverse of the stationary distribution, right? It's irreducible. So the stationary distribution is positive, and so the inverse is well defined. So this is true. This is n, and it's n because 1 over n, the graph is regular, so the stationary distribution is just uniform. This is n, and another way of writing this this quantity is just by conditioning on the first step, right? So it's 1 over d, the sum. I'm going over all the neighbors x1 of x nod, and looking at the expected time of the random walker starting at x1 to return, to arrive to x0, right? And I'm adding 1, right? Because I want to count the first step, of course. So what I get is that, right, I will take the 1 out. It is some d times, and there's a 1 over d. So what I get is that n minus 1 equals 1 over d and the same sum. Tau x1, right? So another way of stating this equality is just, right? I'm looking at the expectation of the expectation starting from a random neighbor of x nod. So I try to write it with a capital X to indicate that it's a random variable. So x1 is a uniformly random chosen neighbor of x naught. I guess this should be x naught, and this is just the n minus 1, right? And as I said, of course, this quantity is not the expected time from x1 to x0 is not symmetric, right? But on the other hand, this thing held, this equality n minus 1 equal this held for any small x naught. So it's definitely true for a randomly chosen x naught uniformly. So if now big x naught is a uniform vertex, and what we obtain is that the expected value starting from x1 to return to x naught, right, in expectation, right, because x naught, x1 and x naught are random, equals n minus 1. But it's completely symmetric at this point, right? Because now you can reverse the roles of x naught and x1. And what you got is that the commute time between x0 and x naught is exactly 2n minus 1, right? And this was to remind, in the commute time identity tells you that this is just twice the number of edges times the resistance. Times the resistance between x naught and x1. So you divide properly, and you get Foster's theorem, right? But with this approach, you can easily see that you can get this for any k-step random walk simply by replacing this sum. Instead of if I had a k-step random walk, I would have written here 1 over d to the k. I would sum over k neighbors, xk minus 1 up to x1, and write the same thing. Instead of a plus 1, I will have a plus k. These are, and I'm thinking about k as a constant, right? So similarly, you get perhaps with a different error, right? Not minus 1. Similarly, you get that the expected resistance between x naught and xk is also 2 over d, 1 plus little o of 1. And all the little o of 1s that are hiding here, they of course depend on the constants k, and they're all also of order 1 over d, right? So there's nothing too clever hiding. So this is in fact the o of d to the minus 2, if you care about the errors precisely. So this is one extension that is cute. So this is the end of this proof. And the second extension that I want to show you, it will perhaps not be exactly clear why it is an extension. But first, are there any questions about this proof? Okay. I mean, I guess the question that could be on your mind is, what does this have to do with what we're trying to prove? And I promise I will tell you if you bear with me a little bit. Here is the last extension. I will write it as a theorem, not because it's so more serious, just because it'll just be easier for me later. And so before the theorem, let me say the remark again, with high probability on the random walk, k-step random walk, right? So k is fixed. With high probability, the effective resistance between its endpoints is of order 2 over d. Okay, so this is the same kind of reasoning as before, because you have a uniform lower bound. And now let's do something a little bit more tricky. Now I run a k-step random walk. Right? So x node. Oh, right. So let's just do it this time. x1 to xk. So the reason that I used x1 in all of the above was just a mistake, apparently, because my notes switched to 1 instead of k. That's fine. Let's say k bigger than 2, and here is the statement: the effective resistance. So with high probability, as usually on the random walk, the effective resistance between just the last step and the first k-1 vertices of the walk, right, is the following. It is k divided by k-1 times t times 1 plus little 1. Right, so when k equals 2, we get the exact the 2 over d that we got in Foster's theorem, and this is the statement that I'm about to show you. And the first thing that you may wonder to yourself is why do I get this strange number? And well, the first thing when you want to convince yourself that this is the correct number, perhaps you would like to look at the complete graph on k vertices and just do the calculation and compute the, if you have k vertices, so we do the calculation, and I want to compute this is 1 and this is 2 up to k-1, and it's just a graph on k vertices. What is the effective resistance between the vertex 1 and the set 2 to k? Okay, so sorry, so I switched. And obviously here it doesn't matter if I look at x1 to the last k-1 steps of the random walk, or the other way around. Right, so you will have a vertex 1 and it has k-1 edges connecting it to the blob. So you get 1 over k-1, right? This is the resistance. So what does this have to do with this number? Okay, so let's do this slowly, and instead ask a more general question, because notice that we know for every 2 indices, right, in k, we know that the effective resistance between xi and xj is 2 over d plus smaller order terms. Right, so we know the pairwise resistances between any 2 vertices, and we're asking ourselves of the walk, and we're asking ourselves, can we reconstruct a more complicated electric resistance between two subsets, 2 disjoint subsets? Or in general, we can ask an even more general question. Assume I have a network on n vertices, right? And but I do not know the network. I do not know the conductances, but I'm only given n choose 2 numbers, and I'm giving the pairwise resistances for any 2 vertices, not necessarily an edge in the graph. Does that uniquely determine the network? Right. So or a more general question is, so the first question was, does this imply the theorem? Or if we know the Rxy for any x not equals y, for any 2 vertices in a network, can we reconstruct the network itself? So can we tell what are the edge conductances? And then, of course, we can compute everything. Can we reconstruct the network? This is the first question. The second question is, this operation, assuming we can reconstruct, is this operation stable, right? Under, changing one of the or several of the effective resistances between pairs, if we change them by a small epsilon, right? But we're not given the precise effective resistances between xi and xj, right? There's an error there, but an error, perhaps the error accumulates and we get a large difference. So the next question is this stable? And I guess do you have any guesses? Or I did not have any immediate guess, but just as we stated like this, it cannot be true, right? It is false because because I can't, if I know the pairwise effective resistances between any two vertices, I cannot tell if there are any loops in the network, right? Because a loop in your graph will, of course, will not affect these numbers. But up to that, it's indeed possible. So the answer is yes, up to loops. Right, and let's see a cute way of showing this. I'll just prove to you this lemma, and this lemma immediately implies the theorem. And this is a cute lemma. I have a number k, I have a number x fixed. The lemma is tailored exactly for this situation, that we have all pairwise resistances are the same number, but you can prove exactly, you can prove with this with the proof that I will show you, you can answer this question entirely. And the epsilon is small, very small, depending on k and x and perhaps some other things. Then if and you have a network, and you have a network on k vertices, on the vertices, let's call them 1 to k, right? And if the pairwise resistances, right, we do not know the network itself. There's some network there, but all we know is the resistance between I and j is approximately x, right? If this holds for any I not j, not equal to j and k, then the resistance between, and you can reconstruct the network entirely, and in particular, the resistance between one vertex and all other vertices is going to be kx over 2k minus 1. And if you plug in our situation, k is 2 over d, you plug in 2 over d instead of x. Oh, and of course, there's an error here that depends on epsilon. And if you plug in x equals 2 over d, you get exactly this number, the theorem, and you get exactly the theorem, right? I just chosen this lemma particular statement, but the fact is here that you can just reconstruct the network, and then you get this in particular. Also, notice another step that I'm hiding under the rug here, and that is in my setting, in the setting that I am, I have some k vertices, capital X1 to xk, all right, inside a large network, right? So how does this lemma imply the theorem, right? The lemma is just about a network of size k, but I can easily change this lemma and make sure that 1 over k is just a subset of a much larger network, because you can always look at this, like the watched network, the induced network on the smaller set of vertices. So this corresponds to just observing the random walk only when it's on the vertices 1 to k. I will just skip this part, and you can treat it as a nice, easy exercise in electric networks. So let me try and convince you with this lemma. Okay. This is nice. So here's a proof. The proof will proceed in 2 steps. And as I said, this is all just a very casual, nice electric theory business. So the step 1 is the first one, is if I knowing pairwise effective resistance, then we can recover all voltages. So by all voltages, I mean, right, if I have, what do I mean by a voltage? A voltage is always, I take 2 points and consider the harmonic function that takes 0 at this point and 1 at this point, and the voltage at the point inside is just the probability that I hit the second vertex before the other one. And by all voltages, I mean whatever pair that I choose, I can reconstruct the voltage. Okay, and additionally, this recovering is also stable, meaning that if I change one of the resistances by a little bit, no voltage changes more than a little bit, right? And the reason for this is, so let's convince you in this. So here is the voltage. So this is just my definition for the voltage at vertex I. When the voltage is going from J to 0. Sorry, when the current goes from J to A, right? And it is unit current. So let's just say voltage at I, the value of the harmonic function at I, when you put in 0 at A, and at J, you put some other number, and this is going to be unit current. Well, let's just say it's the, you put voltage 0 at A and 1 at J, and I is the value of the harmonic function. Okay, so when voltage at I, when A receives 0 and J receives 1, right? There's just a unique harmonic function. So this is, of course, a well-defined thing, right? This is just the probability when I start from I that I will visit J before A, right? So this is just the same thing. Then this number I can reconstruct via the resistances by the following, and this formula also shows you that this is stable. Minus the resistance from I to J, and I'm dividing by twice the resistance from A to J. Okay, so this is a formula. I would not guess this formula if you just tell me, if you just show me this formula. It's hard to see why it is correct. I will show you in a second, but at least you can convince yourself that as it should be, that the numerator is non-negative, right? Because and the fact that it's non-negative just follows because the resistances satisfy a triangle inequality. So what you have in the numerator is non-negative, and so why does this hold? So again, this is an interesting formula, and there are several proofs, and some of them are better than the other. But I like the intuitive proof more. So again, you can just consider, right? For this formula, only involves 3 vertices, right? You can just look at the chain watched on these 3 vertices A, I, J, and convince yourself that this kind of statement holds there, and then it will hold also for the bigger chain, because all of these values don't change when you look at an induced smaller chain inside a big chain. So you really have to convince yourself that this holds on a network that has 3 vertices, right? So it suffices to consider a network with 3 vertices, right? So, and then the question becomes just like a very elementary question, but it's still not entirely trivial, right? So this is the situation that we have. Let's call them instead of A, I, J, I'll just call them the 3 vertices 1, 2, 3, and I have conductances C12, C13, and C23. These conductances I do not know, right? I want to recover them, or I want to recover the voltage, and I'm giving the effective resistance between the vertex 1 and 2. And of course, I can compute it here because I can just use the parallel and series law. So here I have from 1 to 2, I will have two parallel edges. One is an edge with the conductance C12, and the other is an edge that its conductance or its resistance is the sum of the inverses of the conductances. So what I get, right, is that the effective resistance is just 1 over C12, right? The conductances add in parallel and resistances add in, what's the opposite? In series, right? So C12 is something that I add to this 1 over, right? So this is the formula that you get immediately if you just plug in. If you plug in the series, the series and parallel law, right? And of course, you have three other formulas, right? And you ask yourself, right? I have three unknowns, right? These conductances. Can I always solve these three equations? Of course, they're not linear, so it's not immediately clear that for any choice of these three numbers, effective resistance between 1 and 2, 2 and 3, and 1 and 3, that I can always solve this, right? Perhaps Rick sees an algebraic way of seeing it immediately, but or some fancy theorem, but a nice way of showing it so it's indeed it can always be solved. And one nice way of showing it is using a Yang-Baxter move. So a lot of statistical physics model has this secret magic that allows you to a secret move that allows you to see things much better. And it turns out that this Y delta transform in electric networks is exactly the key. So it turns out that any network on 3 vertices or more is always going to be equivalent to a network with 4 vertices, but the only edges that you have are edges. There's a vertex in the middle that I'm not giving any name. The only vertex that you have is the only edges that you have are edges between the 3 outside vertices and the 1 inside, right? And it's equivalent in the sense that all of the effective resistances are the same, and between any 2 vertices, and it's an equivalent network in a sense. Then once you put this network like this, it becomes much easier to solve, right? Because the effective resistance between 1 and 2 is just R1 plus R2. The effective resistance between 2 and 3 is just R2 plus R3. And this, the last one, of course, is just R1 plus R3. So on the right-hand side, you have an invertible matrix, right? And you're looking for solutions in R1, R2, and R3, right? And the matrix is invertible, right? The matrix is just a 1, 1 node. Yes, I wrote it like this or anything like that. The matrix is invertible, and hence there is a solution, right? And that's it, right? So what you're looking for, right? And our goal was to prove something like this, right? So let's assume. So let's say that I was 3 and A, J are 1 and 2. And so you invert the matrix, and right, it turns out that it's just a matrix that has a half or minus half at each of its entries. I will not. Do you want me
So
to?
how do you? So is it obvious that inverting the matrix gives positive resistances?
No, it's not. Yeah. But you
so
invert the matrix.
There is something more here then.
Sorry.
Yeah,
Sorry.
So there's something more here. So something more needs to be said.
Eventually you get a formula like this, right? You want to find out what R3 is. For instance, I did this matrix inversion in my notes, but I won't bore you with that. you get this, right? Big capital R is the effective resistance between 1 and 2. Right? It is not immediately clear, right? But once you see a formula like this, right, you immediately understand that the numerator has to be positive, right? So it's not clear, but it's a fact. It turns out that you always get something positive, right? I don't know the answer to your question. If I just look at this matrix, do I see that and I want to solve an equation of this form? Is it always are the solutions always positive? I don't have a reason, but I know that this is.
You said earlier, though, Asaf, you said that the effective resistance satisfy a triangle inequality, and that's where you're using it here to get the positivity.
Yeah, no, but what Omer asks is like, can you look at this matrix and immediately say that if you want to solve the linear system with the solution positive, then with these values positive, does it imply that these are positive just by looking at the matrix? I don't know the reason for that.
Well, it's not true. But it's not true.
I know it's true, but I don't know how to just look at the matrix and infer that.
But it's not true that R's have to satisfy the triangle inequality, or else you won't get positive little r's.
Right.
Yes. So
sorry,
given the triangle inequality, this is fact.
Yes.
That's the extra ingredient.
Yeah. Right. That's correct. Okay. So where were we? Step 1, right? We the lemma was I want to reconstruct the graph, and what I reconstructed so far is the voltages, right? So and step 2 of the proof of the lemma, right, is to show to you that knowing the voltages allows to recover the graph, the network, the entire network, allows to recover the network. And this is not very clever. And this is, for any probabilist, this should be obvious. And the reason is that the voltages are proportional to the green function, right? The green function is this harmonic for the green function properly normalized. And the green function, as we all know, is the inverse of the Laplacian matrix, right? And the Laplacian, if we know the matrix, then it's exactly what we're looking for, right? So this is familiar to everyone from the continuous setup, but in the discrete setup, it works just the same. So if lambda, sorry, what is this letter? Laplacian, this is delta. My Greek is always so delta ij is the Laplacian matrix, meaning that it's minus the conductance if I is not j, and if I equals j, then I just put here the pi, the sum of the conductances, edge conductances coming out of I, and if A is some fixed vertex, and I look at the right, this is pi, and I'm erasing the row and column. I'm taking the minor at index A. Then it is just the definition of harmonicity that this matrix is the inverse of the matrix V A I J. Okay, where VAIJ is what I've defined before. Perhaps I should normalize VAIJ to not have this, right? So if it was unit curve, so it's not exactly the same up to this factor, right? So and it's not IJ, right? So this I'm just considering it as a k-1 up to k-1 vertices. So this theorem also tells you that this matrix is invertible, right? Which is not obvious at all. So if I know all the voltages, then I can reconstruct the Laplacian matrix, and in particular, I can find out exactly what are the edge conductances in the network. And the last question was, is this operation stable, right? And this is just a fact in linear algebra, right? So this is an easy fact. You just get expanding from the usual geometric expansion. Right, so the fact is that if A is invertible, and E is a matrix with very small entries, small in terms of many things, K, epsilon, the values of A inverse with small entries, right? So I'm not saying small with respect to what, then A plus E is invertible and close point-wise, close coordinate-wise, to A minus 1. So adding a little bit of error to an invertible matrix keeps it invertible, and the two inverses are not very far from each other, right? And this, so now I will just conclude, because right, what is the situation that we have here, right? So the situation here is that all of the resistances are X, right, with an error, and hence all the voltages, right? So if I look at the, where am I? Right, so the voltages are going to be off diagonal, are going to be, right, 2x minus x, that's x over 2, and on the diagonal, right, they're just going to be x, right, because ij, this one is going to vanish on the diagonal, so the plus an error. So the matrix that I want to, the matrix VA is just a matrix of the form x on the diagonal and x over 2 off the diagonal, and when I invert it, so this is that. When I invert it, right, that's just an easy calculation that I get 2k minus 1 divided by kx on the diagonal, and minus 2 over kx off diagonal, right? And for this, and this is exactly what and this, once you know this, you can immediately find out the effective resistance in your network on k vertices or more between any two sets, right? I just chose one particular type of a pair of sets, just a singleton and the complement, all right? And you get immediately that this should be, right? One way of seeing this, right? If I erase the loops in my network, right? This is 1 and this is 2 to k. If I erase the loops, then the random walker in one step will reach the set 2 to k, and that's why the resistance is just 1 over the corresponding pi of 1, right? Then the sum of the conductances coming out of 1 once I erase the loops, right? So this is just the sum of j over 2, j from 2 to k of Cij, right? And C1j, right? And all of these values are, these conductance, edge conductances are 2x over k, right? You have the minus sign because the Laplacian puts a minus off diagonal. And this is just exactly what we were hoping to get, right? So x, so this is just 1 over k minus 1 times 2k over x, which is exactly what we were trying to obtain. And so together with this linear algebra effect, we get the lemma, and we get this rather peculiar theorem about resistances of a, between two random sets, and this way. And I guess the question that remains, what does all this have to do with uniform spanning trees? And this I will show you to keep your curiosity alert. I will show you on Thursday, in the first 15 minutes, I will show you how this immediately, or with some work, not very sophisticated, not very sophisticated works, gives you the theorem that I hinted before. There's one issue is tightness. I will not show you because it's a little bit complicated, but once you have this, somehow this kind of statement, right, the statistics of the resistance over randomly chosen sets in the graph allows you to find the local limit of the uniform spanning tree. So this I will show you in the first 15 to 20 minutes of my last talk on Thursday. So thank you for your attention. Thanks, Peter.
Thank you.
Hi.
Yeah, so we will stop the recording and we have time for questions.